All right, let's get started with feature engineering. So I have PyCharm open and feature underscore engineering.py popped up. If you have ever done any data science, you know how critical feature engineering is. So one type of data set that we often deal with in data science is what's called the time series data set. So it's time aware data. And with this type of data, we clearly have to make sure we're not introducing feature leakage, or in other words, we are not leaking information from the future that we would not have actually known as of a certain timestamp. So, for example, we need to make sure that if we're doing any calculations specifically for machine learning for something on January the 2nd, we don't include any information from any of these future dates. And so what I've done is I've just generated a synthetic, very simple time series data set that has a date column, a group column, and a value column. So let's say that we wanted to calculate the mean of each group. Well, again, because this is a time series data set, we would not just want to do like a simple group by each of these groups. We need to do something that's a little bit more sophisticated. So what we do is an expanding mean. So this will take basically this first data point and the group and say, okay, what is the mean that I would have known at this time? And so this should become self-apparent if I run this. So we can see that, okay, for group A here on January 1st, the value was 10. The mean is also 10. On January 2nd, the value of A was 10. Therefore, our expanding mean then becomes 15. So we can see that again, the first time B appears, the value is the same as the mean. So we're careful not to leak information from the future. At each row in the data, which is time aware, we are only factoring in information into the mean calculation that we would have known at that point in time. And this is, again, very important when we're doing machine learning. We need to make sure that we are not allowing ourselves to cheat by leaking information from the future. All right, so one more example on this. Let's say that we wanted to do something slightly more sophisticated, that we didn't just want to take an old, plain, boring mean, that we wanted to do something customized. So we can do something called a clipped mean. So what we do is we progressively calculate what is a lower bound and an upper bound, which I'm just defining as a quantile, and then we clip the series based on that. So if the current value is below this quantile value, then just set it to the quantile value and then take the mean of the series. So I generate a slightly larger data set, again, something that's very simple, goes from the 1st of January to the 10th of January. We have some groups in this calculation. We actually don't care about those. And then our value, which is what we actually want to calculate the mean of. So again, we're doing this clipped mean. This could be some other version of the mean that we want to do. This is just kind of an example. So again, if we want to calculate just a plain mean with a time-aware data set, we need to do an expanding mean. And once again, if we want to do the clipped mean to be okay with time-aware data, we need to make sure that it's expanding. And then we can use the apply method to then apply the clipped mean. So I am going to run this, and we'll see some output that will make this a little bit more concrete, I think. So first of which is we can actually view the output of the data set. So we have our expanding clipped mean and our expanding mean. So if you look across here, you can see that these are very close, but they do differ in different areas. So we can see that especially here at the end, the expanding clipped mean is actually a little bit lower of the expanding mean. So this did not produce the exact same results. Obviously, if we had a data set of hundreds or thousands or hundreds of thousands of records, you would see likely more variation in these numbers. But the proof point is that these did produce different numbers. So we actually kind of to the console printed what is the expanding lower bound and the expanding upper bound. So again, this is looking at each row of the data set and updating these numbers. So on the first row of the data set, which is just 10, the upper and the lower bounds are 10. So you can see that as we progress through rows in the data set, which is what the apply function does essentially when we combine it with this expanding capability, that these numbers are dynamic. And so because we are dealing with an ordered data set going from an older date to a newer date, this expanding window for the clipped mean does work as appropriate. So again, we can see that the expanding clip mean is different than the expanding mean, and we can see how dynamically the upper and the lower bounds change as this basically iterates over the data frame, the expanding applied with the combined with the apply function, I should say. So again, the summary is that whenever we're doing anything with a time series with data science, we want to make sure that we are not leaking information from the future. So therefore, these expanding types of windows and these expanding functions, combined with an apply function to do something a little bit more sophisticated, can definitely be something that's very powerful and ensure that we are engineering features that are realistic for the timestamp on each given row.